Hello everyone. So in this lecture I'm going to talk about introduction to group theory, and I'll try to give some intuition behind it, like why we are defining the definition like that. So I'll begin with an example of symmetry of an equilateral triangle. So consider an equilateral triangle 1, 2 and 3. What are the possible symmetries of this triangle? What do we mean by the symmetry is just some motions that pick this triangle up and put it back down so that it occupies the same space. So some possibilities are rotations. So considering three of them that are possible is row 0, row 120, row 240. These are nothing but rotation by 0 degree is nothing but just keeping it as it is, and rotation by 120 degree and rotation by 240 degree. So this will give, I'll just draw quickly here. This 0 degree is nothing but the same thing, this thing. So I'll not draw that. I'll quickly draw the second and third one. So this will give 1, 2 and 3, and this will give 1, 2 and 3. Yeah, something like that. So yeah, what are the other possibilities? So we can simply see here, we can draw some axis. See this new one and new 2 and new 3, and we can list three other symmetries, namely 4, 5 and 6. That is new 1, new 2, new 3. It's nothing but just a flip. So what are the symmetries here? I'll quickly draw here is 1, 3, 2, 3, 1, 2 and 2, 1, 3. Yeah, these ones. So these are the three possible symmetries of equilateral triangle, and you can simply check there are no other possibilities. So what else now? We can simply check that it's not necessary that. So yeah, before going to that towards that direction, I'll say how you'll think about composing these operations. Maybe I'll ask you about row 120 composed with new 2. It's nothing but applying new 2 first to 1, 2, 3, this equilateral triangle, new 2 to this, and then apply row 120 to the resultant triangle. So yeah, it's simple. It's nothing new to you. It's nothing but just a composition of functions. Yeah, and we can see it's not always commutative. So composition of any f o g is not always equal to g or f here. So yeah, it's a point to note. So yeah, here we can see intuition behind some operation and like composition of those operations, and they are not always commutative, and some idea behind it. Yeah, now going towards some formal definition of a group. So, formal definition of a group. So, the example gives us a blueprint for the general definition. A group is essentially a set of action that we can combine, reverse, and then includes a do nothing action. Let's write the formal definition now. So, a group is an ordered pair G star where G is a non-empty set and star is a binary operation. And how star is defined? It's defined from G cross G to G. It will take two elements of G. It will apply whatever operation it is defined as, and it will give an element in G. And it satisfies three axioms. What are those? So closure is already covered here because it's a binary operation as defined like this. It will always give an element in G, so it's closed. And what are the other operation and axioms that it should satisfy? Not operation, basically axioms. So the first one is associativity. That is like apply for all A, B and C belongs to G. If I'll apply A star B and then I'll apply C, it is equal to A star B star C. For any ABC engine, it should satisfy this. Yeah. The second one is identity element. So what does it mean? There exists an element E belongs to Z such that for all A belongs to G, A star E is equal to E star A is equal to A. Basically a element E, and if we apply, like if we'll operate E with any other element A, we'll get A. So A, there exists such element E in G always, such that it should happen. Yeah. And of course an inverse element. The third and the important condition is inverse element. Every element should be invertible. For all A belongs to G, there exists some B belongs to G such that A star such that A star B is equal to B star A is equal to a identity, the same identity that we talked about in the second axiom. So what happens if the operation is commutative? Like a new condition I'll introduce, commutative. What if for all a comma b belongs to G, a star b is equal to b star a? Then we say G is abelian group. Yep. Abelian group. We can see in our example we were talking about here about associativity, identity, and inverse. Associativity is very easy to check, and I leave that for you. You can easily verify if any operation, like try to operate like this. Maybe, yeah. Try to apply row 0 with row 240 and then new 2, and then check that if it's equal to row 0 into row 0 row 120 new 2, and check if it's equal to row 0 row 120 new 2. Check and check with like other operations. It's basically calculation and composition of function, and it's easy to check. I'll leave that. And what should be the identity element? Like which operation you think that will act as an identity? Like applying that with any other operation will give just that operation. That should be rotation by 0 degree, because it's basically doing nothing, just keeping it as it is. So that should be the identity element. And what should be the inverse element? So for inverse elements, for you can easily see for mu1, mu2, and mu3, if we apply mu1 again, like apply mu1 twice, we'll get the same thing. Like applying mu1 twice on this triangle will give this triangle again. So what should be the inverse for mu1, mu2, and mu3? Similarly for mu2 and mu3, if we'll apply twice, we'll get the same triangle. So what should be the inverse of these elements? That should be the same thing. Like for mu1, the inverse is mu1, for mu2, the inverse is mu2, and for mu3, the inverse is mu3. What should be the inverse for rotation of 240 and rotation by 120? So for rotation by 120, the inverse element is rotation by 240. You can easily check composing row 120 with row 240 is nothing but row 0, and row 240 row 120 is row 0. So these two are inverse of each other, and inverse of row 0 is row 0 because it's basically doing nothing. So we have verified here like that these set of 6 functions or operations are well defined for the definition of group. So we have successfully defined the definition of group, and we also got an intuition behind the definition of group from the symmetry of equilateral triangle, and we have seen how and why we have defined the definition here like this. Now groups, can we think of some other example of groups? Let's talk about some examples. So the very first one that comes to my mind is Z plus. So it's really easy to see that addition is a binary operation, because adding any integer will give you integer. It's easy to check the associativity. Now talking about the identity and inverse. So identity should be, in terms of addition, it should be 0, and inverse for any n, it should be minus n. I'm not writing the details. You can write it on your own. So now let's see this one. Z with respect to multiplication. What should be the identity? I think it should be 1, if I'm right. Yeah. What should be the inverse? Oops. For 2, we need 1 by 2. But 1 by 2 doesn't belong to Z. We don't have inverse for 2. Inverse doesn't exist for 2 belongs to Z. Therefore, Z is not a group. Z is a group with respect to addition, but it's not a group with respect to multiplication. What are some other examples? Some typical one, not so basic one, maybe. Yeah. Example that comes to my mind is GLNR. What is this? Basically, all matrices of n cross n order such that determinant of A is not equal to 0, that is A is invertible, and entries of A's belongs to real numbers. So of course, we have defined this set of elements, set of matrices, so that they are invertible, and with respect to multiplication, they form a group. So yeah, we have talked in this lecture, we have talked about intuition and behind the definition of groups, and how we can think, like why we are defining using the symmetry of equilateral triangles. Then we have formally defined groups, and then we have talked about few examples and few non-examples also. Few not, but yeah, a non-example in this segment. So in next lecture, maybe I'll try to introduce about a concept that is a subgroup, and maybe I'll talk about subgroup tests, like how we can check if a subset of a group is a subgroup or not. So yeah, thank you for watching the lecture.